Hey everybody, it's Ripley back again. We're going to talk a little bit about product and quotient rule today. Good times. Now, if you recall, we know that the derivative of a product is not equal to the product of the derivative. Otherwise, every derivative would be zero because we know the derivative of constant, right? If I were to take the derivative of 3x, for example. Well, we know that's 3, but if the derivative of a product were the product of derivatives, then it would be the derivative of 3, which is 0, times the derivative of x, which is 1, and that would give me 0. Frowny face. That doesn't work because we know it's not true. Okay, so what we have is this really cool little geometric way of proving the product rule. We could do the same for quotient rule, but if I have something called the chain rule, which we'll talk about in a few sections, then that makes it a heck of a lot simpler to prove the quotient rule, and I'll do that in subsequent videos. All right, so first things first, I want to point out a couple things. I want to point out that I'm letting u be f of x, okay, and I'm going to let v be g of x, okay? And then delta u is just a change in u, right? And we can think of that as f of x plus delta x. So we add a little chunk of x, a little change in x to x, and then we subtract f of x. That makes sense, doesn't it? This is just basically a change in f. Likewise with g. All right, now why don't we use f's and g's? Because it's just kind of easier to look at this sort of geometrically if we sort of remove ourselves from these two facts for a second. All right, so here's the original u value and here's the original v value. And if we think of their product, then we can build that geometrically as the area of a rectangle. Delta v is going to be a little bit up this way, right? We just got a little chunk that we're adding on, and then delta u is going to be a little chunk that we're adding on this way, okay? So what we're doing here is all of these four little lattices, or parts of this lattice, these cells, if you will, are representative of areas. This guy is u times v, this guy is u times delta v, et cetera, et cetera. Now, what I am looking for when everything is said and done, I am looking for the, oh, orange, yuck, the derivative of f times g. That's what I'm looking for, okay? Now, before we get too heavily into this, I have got to change that color, sorry. Before we get too heavily into this, let's look at what that really means. What we're looking for is the change, the delta of u times v, right? I mean, if we think about our fishing expedition, right, we start with a big change, which we can call delta, and then at some point we're going to take a limit, we're going to shrink this thing down to a d using Leibniz notation. Well, do you agree that the delta of u times v, the change in this, as v and u change a little bit, becomes, well, it's going to be all of this part, all of this part, now I should have used the orange, right? Right there, which is going to be u times delta v plus v times delta u plus delta u delta v. Pretty straightforward, right? Nothing to it? All right. Now I'm going to use algebra. Since we know that these are functions of x, it's pretty simple for me I can do anything I want to the equation as long as I don't divide by 0, right? Or turn anything into infinity accidentally. So what I'm going to change colors here, and I'm going to divide everything through by delta x. I've broken no laws. I know that delta x is a positive change, right? Or I guess it could be a negative change too, but we don't really care. So I've broken no rules. It's not 0. Everything's good. All right, let's do some more algebra. Now I'm going to go back to blue, and I'm going to take the limit of all of these things. Well, what am I going to take the limit of? Well, if you recall, one way to define f prime of x is the limit as delta x goes to 0 of delta y over delta x. That's one way to do it. So I'm simply going to apply this definition to this equation. Again, I can do whatever I want and still break no rules as long as I do it to both sides, right? Or I add 0 or multiply 3 by 1. So I'm going to take the limit as delta x goes to 0. I'm going to be lazy here. I'm going to be super lazy. Of delta u times v, I'll put that in parentheses, over delta x. Now, that gives us exactly what we want. Because remember, f prime of x can also be defined as dy over dx, or whatever this d chunk is on top. So I know in my next step, free of charge, I have d over dx of u times v, which is equal to d over dx of f of x times g of x. Whoops, g of x. Sorry, I'm writing in my belly button here, so bear with me. Okay, so I got that for nothing. That's free of charge. So I'm going to go limit as delta x goes to 0 of u times delta v over delta x plus v times delta u over delta x plus delta u times delta v over delta x. All right, easy peasy. Nothing to it. Well, let's look really closely, just for a second. What can I do? I'm going to change colors is what I'm going to do. Notice this chunk, this thing right here, if I use this definition of a derivative, isn't this guy just dv over dx? Just the derivative of v with respect to x. And you may say, whoa, Ripley, what are we doing with u? Well, u doesn't have a delta x anywhere near it. It doesn't have a delta. So it's just a constant. As far as that limit is concerned, that u is just a constant along for the ride. So I can write this as u times, well, what would that be? This would be dv over dx plus, similarly, the limit of the sum is the sum of the limits. So I can distribute this limit across. This is going to be v times du over dx, right? You see what I'm doing here? That v is a constant as far as this limit is concerned. This guy, according to this definition, is just du over dx. Now, this one's a little trickier. We got to talk a little bit about this. So what I'm going to do is, excuse me, I'm going to write this as delta u, times the limit as delta x goes to 0 of delta v over delta x. Whoa, sorry, I got a little crazy there. What am I doing with my delta u there? We're going to put that guy inside. I want my delta u, oops, sorry guys, delta u right there, because the limit of the product is the product of the limits. Okay, so let's pick some low-hanging fruit right now. Okay, remember, u is f and v is g. So I can write this as f of x times g primed of x plus v is g and u is f. So I can simply rewrite this as f primed of x times g of x. Now I got to deal with this guy. All right, so the limit of the product is the product of the limits. So the first limit that I get for nothing, I'm lagging here. Bear with me for a sec. I don't know why I'm lagging. All right, we're back. Sorry. I know that this guy can be written as dv over dx, which we could also write as, what's v? G primed of x. But let's look at this. What is the limit as delta x goes to 0 of delta u? Well, that's up here. If I take the limit as delta x goes to 0 of delta u, isn't that equal to, well, look close. If delta x goes to 0, isn't this just f of x minus f of x? Because this guy just turned into a big fat 0, which is 0. So this is going to be times, whoops, there should be a plus there. This is going to be times 0. So this whole term drops out. Hey, guess what? We have something. The derivative of a product is equal to the derivative of the first times the second as it stands, plus the first as it stands, times the derivative of the second. That's it. That's all it is. Now, you could remember the commutative property of addition says you can change the order in which this is done. I think that's sort of how I wrote it down here, isn't it? But I used commutative property. For me, it's easier to remember the derivative of the first. Do that thing first. All right? So, for example, if I want to take the derivative of the square root of x times, let's go 4 to the x. Well, if you recall from the past, hopefully you have memorized this because it'll make your life easier. The derivative of the first, the derivative of the square root of x is 1 over 2 root x. We've memorized that. Times the first as it stands, plus the first times the derivative of the second. Well, what's the derivative of 4 to the x? The derivative of 4 to the x is 4 to the x times the natural log of 4. Okay, now this is a really important thing to understand, because students always ask me this, and it's a super valid question. For example, they will say, Ripley, how far do I have to take my derivatives? In other words, algebraically, should I factor out a 4 to the x? Should I don't know, find a common denominator of root x? Here's my general rule. take it one step algebraically past. Here's the problem right now is you're learning scales as if on an instrument. You don't know that those scales are going to turn into tunes. So you don't really know what you're doing with these derivatives yet. There will come a point where you will know exactly how far to take your derivatives because that's when they're most useful. But for right now, leave the derivatives after one step or so. Now, there's a notable exception. For example, let me say that I want to do, let's make it interesting. I want to do 1 over, oh man, why is this thing lagging? 1 over x times e to the x. And then I'm going to do plus, let's go plus the fourth root of x cubed. Okay? I want to take the derivative of this guy. All right. So, first things first, we got to remember that all other rules are not somehow superseded by a new rule. They're still fully in effect. So I know that the derivative of the sum is the sum of the derivatives. However, there's a product sitting right here. So the derivative of the first, 1 over x, hopefully, again, you have memorized this, is negative 1 over x squared times e to the x plus the first as it stands times the derivative of the second, which is just e to the x. Now that takes care of this first term. All right, now the other thing to remember, let's change colors real quick, is this can be written as x to the 3/4, right? This guy right, this guy right here. So when I take its derivative, I can write this as plus 3/4 x to the, I subtract 1, negative 1/4. Now, theoretically, mathematically, calculusly, you are done. You have taken a derivative. There are no more derivatives to take. There's nothing more to do. However, to be able to use it, we want to be able to change it around algebraically. There's another little rule that I have with derivatives, and that's this. If I started with a square root, finish with a square root. This is a radical expression. This is an exponential expression. So what we want to do is we want to put this guy into the radical expression just to make it look pretty. All right. Now, I wouldn't worry about finding common denominators yet or factoring out e to the x's out of this yet. I would just pretty it up and I'd do something, I don't know, I'd probably go e to the x over x minus e to the x over x squared plus 3 over 4 times the fourth root of x. And be careful with my notation here, right? This is the fourth root of x, not 4 times 4 root x. Okay? That is how we deal with, things like radicals, things like logarithms, things like that. We want to put them back in their original forms that we started with. If we started with an exponential form rather than a radical form, just leave it in an exponential form. I would just always get rid of that negative if I could, because it'll make my life happier. Okay, now that's the product rule in a nutshell. Let's talk about quotient rule. All right, so now I'm going to take the derivative. Now this one, I'll show you. This is going to be f divided by g. I'm not going to go through the same geometric proof that I went through in the last one. However, you could if you wanted to. The thing is, it's much easier to prove the quotient rule once we have chain rule. And chain rule's coming. It's in the pipeline. It's a couple sections down the road. So I'm not going to waste your time and my time doing that. I'm going to wait for chain rule, okay? Suffice it to say that the quotient rule is the derivative of the top, if I have something being divided by something else, the derivative of the top times the bottom as it stands, minus the top by itself times the derivative of the bottom, all divided by, and this is the most counterintuitive thing that you're going to see for a while, the bottom squared. Okay? Now, excuse me. Let me show you how this works. I'm going to give you an example. However, there's a mnemonic device that you can come up with, and that is low d high minus high d low. Kind of high d low, high d ho, but high d low. Whoops, that wasn't supposed to happen. Over low squared. Low to high minus high to low, all over low squared. All right? It makes where you're going to get screwed up on this equation is right there, that negative. You're going to forget which goes first. The way I always remember is it just makes sense to take the derivative of the top first. The numerator should be differentiated first. Why? I don't know. It just feels intuitive when I do it. Okay, so you're always going to go low d high, or the derivative of the top times the bottom as it stands, minus the top times the derivative of the bottom divided by the bottom squared. Not the derivative of the bottom squared, just the bottom squared. Don't get crazy. Now I want to give you a couple of examples here. Let's keep this one simple. Let's go 1 plus e to the x. What am I doing? Let's go y equals 1 plus e to the x over the square root of x. Okay? Now this is when that little warning from last section really comes into place. Like, how much extra do I have to do? And again, if you were sitting in my class, I would take it one step algebraically further than when you take the derivative. Okay? I'll show you what I mean in just a second. All right, so here we go. Y prime is equal to low d high. All right? So the derivative of the top. Well, what's the derivative of the top? Well, 1 plus e to the x. Derivative of sum is the sum of the derivatives. 0 plus e to the x. Okay, that's going to be e to the x times the square root of x, minus high, 1 plus e to the x, respect thy negative, remember this is a parenthesis, times the derivative of the bottom, which is 1 over 2 root x, all over the bottom squared. Well, that makes things nice, doesn't it? Now, this is a little bit ugly. And this is kind of one of those where I'm going to let you use your prerogative, what you think looks good. Okay? If I wanted to, I could write this thing as e to the x, I don't know why I put an e there, that should be e to the x times root x, let's see, however, I've got a 2 root x here, so you see, what do I do here? I could put a 2 here and get rid of the root x, couldn't I? If I found a common denominator, think of the common denominator in the numerator, so ignore this x for a second. Hopefully everybody understands where this x comes from. It's the square root of x squared, right? Common denominator would be 2 root x. So what I would get is, let's make this pretty. What I would get is 2 root x over here. I'd have to multiply the top by 2 root x, which would give me 2x e to the x minus 1 minus e to the x. The whole thing would be over 2 root x, and then the whole thing would be over x. Right? So I could take it one step further if I wanted to and write this as 2x e to the x minus 1 minus e to the x all over. And remember, this guy multiplies the numerator of the denominator multiplies by the denominator of the numerator, right? Skip, flip, and multiply, whatever mnemonic device you need to remember that. Or you could simply write this as 2 times what? The square root of x cubed. Now, that's it. It's done. That thing's finished. And these can get pretty complicated and confusing. And as always, the trick around that is to just do a bunch, okay? Now, what I would like to do is remind you of the fact, again, that just because you have a new rule, it doesn't supersede all of the knowledge, all of the mathematics, all of the algebra that you've had before. You may use your tricks to be able to figure out how you want to proceed. For example, let's say that I want to take the derivative of 1 plus x to the 4th over the square root of x. Now, if I wanted to, I could use quotient rule. This is clearly a quotient rule. But I could also fly to Vegas by way of Detroit. There are sometimes easier ways to do this. I can think of this as 1 plus x to the 4th over the square root of x, over a common denominator. So I could think of this as the derivative of x to the negative 1/2 plus, well, you ready? X to the 4th divided by x to the 1/2 is x to the 3.5, which is x to the 7/2, right? This is x to the 7/2, right? X to the 4th divided by x to the 1/2 is x to the 4 minus 1/2, which is 3.5, which is 7/2. Now look how easy this is. No quotient rule necessary. I would say if you could avoid, if you're not being forced to use the quotient rule, then don't use it. It's pretty onerous, and there are lots of places for you to make errors. So use your better judgment. Use the algebra that you've learned to make your lives easier. This becomes negative 1/2 x to the negative 3/2, right? Plus 7/2 x to the 5/2. And I'm done. I took a derivative. However, Dr. Ripley, you said that we need to turn it back into square roots. You're exactly correct. So I would want to write this as negative 1 over 2 root x cubed, right? Because that's what x to the negative 3/2 is, plus 7/2 the square root of x to the 5th. And I reckon you could pull out x squared here, but then you got absolute values. You could pull out x to the 4th, but then you got absolute values that you got to deal with. Just leave it like this. It works. I can plug values in. And again, I don't mean to sound glib, but right now you don't know when to use a derivative or how to use a derivative. All I'm doing is teaching you how to take a derivative. I will show you their use down the road. For the next few sections, all we care about is making sure that you know how to take them and take them correctly. Okay? All right, that's it, man. That's all we got for this section. I hope you liked it. You're going to do a bunch of them, so you better like it. Have a really good day, and I'll see you in the next lesson.